All right. If you are on Zoom, please take a moment to type something into chat to let me know that you are here while I pass the roll sheet around for those who are physically here. So today we are going to wrap up op amps. I'm not muted, right? No. All right. See what I'm doing. All right, so today we're going to wrap up op amp circuits by talking about input bias currents, finite bandwidth, slew rate, and finite input and output impedances. So let's start with input bias currents.
Dr. Hartman, you're not sharing the screen.
All righty, thank you for that. All right, all I have written is literally the word input bias current, so you guys aren't terribly behind. Thank you. And stop the video. Okay, sorry, or that video thing's going to be up and it's going to drive me nuts. All right, so while an ideal op amp has no current flowing into or out of either of the input terminals, real op amps do have some small amount of current. For a MOSFET-based op amp, this is due to leakage of what are called electrostatic discharge protection circuits, which are effectively specialized little diodes that prevent you from being able to build up enough static charge to touch a pin on the amplifier and effectively break down the gate oxide, the gate oxide layer. Modern CMOS processes are, the gate thickness is so small that literally rubbing your feet on a piece of carpet and then touching a pin is enough to completely fry a chip. And so they build in these little diodes on each of the bonding pads to prevent excessive currents from flowing in either direction, which protect everything. Typically speaking, in a MOSFET-based amplifier chip, the values of these currents are on the order of picoamperes, so very, very small. Pico meaning 10 to the minus 12, okay? For bipolar junction-based transistor circuitry, these currents are significantly larger, and they are representative of the base currents, right? In a BJT, there has to be a current flowing through the base in order for proper biasing to occur. And so we should expect to see that these bias currents are somewhere on the order of microamps, so roughly 1,000,000 times larger than what we would see in a MOSFET circuit. So everything that we're going to talk about from here on out, we're going to assume that we're dealing with a BJT-based op amp circuit, because largely speaking, this effect is negligible in MOSFET-based circuits. So we're going to model these input bias currents by placing a current source between the input terminals and ground. So if we have our generic op amp symbol, like so, arbitrarily non-inverting input on top, inverting output on bottom. Here is our terminal V out. Here is VN1, and here is VN2. We place our bias current, and I'm going to call this guy IB1. Now in your textbook, I have no idea why they choose to put IB2 on VN, the same terminal as VN1, and IB1 on the same terminal as VN2. That makes no damn sense to me. They're effectively equal. It's not going to mess up the math or anything, so I'm going to do the way that makes sense to me and have the same subscript for everything. I feel like it's much less confusing. So this is how we're going to model our input bias currents. And it's going to be easiest to see their actual effects by doing some circuit analysis. So let's consider that we have a non-inverting amplifier. This is our feedback resistor R2. This is our other resistor R1. Over here, we're going to apply our input. Here is where we take our output. So between the inverting terminal and ground, I'm going to see some input bias current IB2. Between the non-inverting terminal and ground, I'm going to see an input bias current IB1. And over here is where I will apply my input signal. So this is what our schematic representation of a non-inverting op amp would look like if we had input bias currents that we needed to worry about. So let's isolate these bias currents and figure out what their effect is by shorting out our input terminal. We want to see what the effect at the output is. So anybody care to venture a guess? Let's start with something pretty simple. We are still considering that our op amp by itself has an infinite input impedance, meaning that this current has to be 0 amps and this current has to be 0 amps. So does the input bias current IB1 have any effect on our output voltage signal? Let's start there. No. Effectively, we have a closed loop from ground to ground, so that current IB1 is just going to circulate in that loop where we've grounded our input signal. So IB1 does absolutely nothing. IB2, however, does do something. So what should we expect our output voltage to be because of our current source IB2? If we're dealing with an ideal op amp, what is the voltage present here at node X? So if we have an ideal op amp, there's no current through R1 because Vx has to be 0. If the non-inverting terminal is at 0 volts, then the inverting terminal also has to be at 0 volts. No current flows through R1. All of IB2 flows through R2, and we observe that V out is simply R2 times IB2. And I'm going to put up here 4 A naught is equal to infinity. So we see some error at our output, right? We have no input voltage applied, but we observe some finite signal at our output. So this behaves very, very similarly to our DC offset voltages, but it occurs for an entirely different reason. All right. So in order to correct this, we are going to kind of extrapolate a few different things. All right. So the first thing that we are going to try is applying a corrective voltage in series with our non-inverting input. And so what I mean by that is, let's do this. Out, R2, R1, here's our feedback loop. IB2. I'm going to apply a voltage here, positive polarity on the right-hand side. I'm just going to call this V correction. Draw IB1. And my input is going to be grounded again. So IB1 is, again, not really doing much of anything whatsoever here. I'm just drawing it to be. So in this case, where we recognize that, again, IB1 is just going to be flowing down through ground and then entering the ground terminal of our input and just flowing in that circular loop, what should we expect our output voltage to be as a function of our correction voltage? Anybody got any thoughts here? So let's use superposition, okay? Let's turn off V correction. What is our output? The exact same thing we have above, because it's the exact same circuit, right? So we're gonna have, oh crap. R2 times IB2. Now let's turn off IB2. What does this thing look like? Non-inverting amplifier, which has a voltage gain, because it's ideal, of 1 plus R2 over R1. So we have V correction times 1 plus R2 over R1. No circuit analysis really necessary, right? We did all the circuit analysis we needed in our previous step. So since we want the corrective voltage to make our output go to 0, it stands to reason then that we can easily say that R2 times IB2 has to be equal to negative V correction times 1 plus R2 over R1. We effectively move this guy to the other side with V out is equal to 0, set them equal to each other, right? That's what we're trying to do. And so we find that our corrective voltage that we need to apply, V correction, is negative IB2 times R1 in parallel with R2. So if we were able to apply a fixed DC voltage of our input bias current IB2 times a parallel combination of R1 and R2, we would completely and utterly get rid of that DC error that we're seeing at our output. The problem is that since our corrective voltage depends on IB2, and since this current depends largely on process and temperature, because it's representative of a base current in a BJT, we have no guarantee that our circuit is always going to operate at the exact same temperature and things like that. So that voltage may shift over time, or the necessary voltage may shift over time throughout the operation of the circuit. which means we're not always going to correct. But we can recognize something else. This is just, the value is just the current multiplied by a parallel combination of resistances. So we can always get this specific voltage by just applying R1 in parallel with R2 at our non-inverting input. So a better way to correct this guy looks like this. Here's R2. Here's R1. Feedback. IB2. IB1. R1, R2, and over here, we apply our input voltage, and again, we're taking our output voltage at the output pin. So I am positing that this methodology will always correct for that offset current that we see. So let's mathematically prove it real quick. Not particularly difficult. I'm going to assign a nodal voltage here, V plus representing the voltage present at the non-inverting input terminal. And since we're dealing with an ideal op amp, that exact same voltage will be present at our non-inverting input terminal, which I'm labeling with a voltage V minus. So the exact same voltage representations that I used way back in circuits 2. V plus for the voltage at the non-inverting input, V minus for the voltage at the inverting input, and because we're dealing with an ideal amp, they represent the exact same quantity. So, what is that voltage V plus going to be in this circuit? I'm sorry, what was that? That would be true if Vn were 0, but let's let Vn be whatever it needs to be. So if we do Kirchhoff's voltage law, we're going to have just Vn plus exactly what you said, right? So we're going to have Vn plus negative or minus IB1 times R1 in parallel with R2. And this is going to be exactly equal to our voltage V minus. If we apply Kirchhoff's current law at our inverting input terminal, we get V minus minus V out over R2 plus V minus no, I'm not, because they are the exact same resistance values. They have to be. That's the whole point. Yeah. If they're not the exact same resistance values, we'll find that things don't cancel out. So I understand your comment, but if I chose different numbers, it would be more difficult to understand. Yeah. Yeah. So they are representing literally the R1 and R2 on the left-hand side are the exact same resistances as R1 and R2 here connected at our output terminal. Yeah. And to this, we add our bias current IB2, set this equal to 0, and with a little bit of algebra, we have V minus over R1 plus V minus over R2 plus IB2 is equal to V out over R2. I'm going to jump ahead to the next page. So this is just me doing algebra. So V minus 1 over R2 plus 1 over R1 is the same as R1 plus R2 over R1 times R2. So let me just go back real quick so you can see what I'm talking about. Too far. All I've done from this step to the next is factor out V minus here. And so I have a factor of 1 over R1 plus 1 over R2, which looks like the reciprocal of those resistances in parallel, right? Because 1 over R1 plus 1 over R2 would be the equivalent resistance. I don't have that 1 over, so that's why I am using, go to the next page, the reciprocal of the two resistors in parallel, okay? And that plus IB2 is equal to V out over R2. I can substitute in my relationship for V minus because V minus is exactly equal to V plus, which gives me Vn minus IB1 times R1 in parallel with R2. So that's R1, R2 over R1 plus R2. This whole thing by R1 plus R2 over R1 times R2 plus IB2 is equal to V out over R2, which gives me Vn minus IB1 plus IB2 is equal to V out, sorry, forgot my resistor ratio there, that's being multiplied by Vn. R1 plus R2 over R1 R2 minus IB1 plus IB2 is equal to V out over R2. So if our input bias currents are comparable, which they should be, because they're both based on a BJT technology fabricated on the exact same chip, these guys effectively go away, and I'm left with, if I multiply both sides by R2, I have R1 plus R2 over R1, which simplifies to Vn times 1 plus R2 over R1 is equal to V out. So putting that particular resistance, R1 in parallel with R2, completely negates the effects of the bias currents while maintaining the transfer relationship of our circuit. So that's a pretty insightful thing. As it turns out, this works exactly the same way for an inverting amplifier as well. So for an inverting amplifier, and I want to be clear here, I'm just going to draw it, but I'm not necessarily going to derive things. We might have something like this. Make sure I have enough room to draw my feedback loop. Here's R2. Here is R1. Here is VN. Here's our current IB2. And then here is our bias current IB1. So in this case, if we were to ground our input signal, we would still see some sort of offset, but that offset can be exactly corrected by placing a resistance R1 in parallel with R2, and we connect that in series with our non-inverting input. So we're always adding the correction to our non-inverting input. And if you go through the math, which I did, but I'm not going to force you guys through, we get a transfer function of V out is negative R2 over R1 times Vn, which means we're completely nullifying the effect of the bias current by doing the exact same correction. So this should be applicable in some shape or form to inverting summing amplifiers, because those are just negative or inverting amplifiers with multiple inputs. They should also be, or we should also be able to do this with a integrator, which is what we're going to talk about next, because we'll see that the input bias current causes our signal, our output signal, to swing towards the supply rails over time if we don't do it. Effectively, this methodology is just how you correct for input bias currents. Always just putting a resistance in series with the non-inverting input. And the value of the resistance is governed by the resistances you have in your feedback and input loop. So let's take a moment to look at an integrator then. So for our generic integrator, negative, positive, V out. We have capacitor in the feedback loop, ground our non-inverting input terminal. Now we're going to have some input bias current IB1 over here. We're going to have our input bias current IB2. Here's our resistor, and here is our input signal. So let's look again purely at the effects of what the bias currents do without any input signal, meaning let's ground this guy. We should again be able to observe that our current IB1 has no effect on the output of our amplifier, right? We're just having current flow in this little ground loop over and over and over again. So that's where all that bias current goes. It's just hanging out around the ground. In order to analyze this, we can observe, or to analyze this more easily, we can observe that our resistor R is in parallel with that current source IB2 when our input is grounded, correct? They're both placed between the inverting input terminal of the op amp and ground, which means they're in parallel. So I'm going to do a source transformation, which is going to make this a little easier to figure out what's going on. So with that source transformation, it's going to put the resistance, that's the wrong color, here in series with the input terminal still, and it's going to put a voltage like so. Since the arrow is pointed down, the positive polarity terminal should be on bottom, negative polarity terminal should be on top. So it will have a value of IB2 times R, just using our good old-fashioned source transformation notes. So now this guy looks exactly identical to our basic integrator. So we should be easily able to see that V out is -1 over RC times the integral of our new input signal, which just happens to be negative IB2 times R. Negative because the polarity of this voltage source is opposite our typical input voltage polarity. Since IB2 and R are constants, good God, what did I just do? No, I don't need to turn in open settings. So when I move negative IB2 to the other side, I get positive IB2R divided by RC. The R's cancel out. The integral with respect to time just gives me IB2 over C multiplied by time. So as time progresses, if our input bias current is positive, we swing towards the positive supply rail. And if it's negative, we swing towards the negative supply rail. So again, we see that having any sort of offset error on our output really messes up how an integrator works. In order to fix this, we will simply place a resistor in series with our non-inverting input terminal. So here's our feedback. The out. Throw a resistor R here that is the same size as this resistor R. Our input bias current problem goes away, assuming that they are identically matched. If they are not identically matched, we put a resistor R2 here to correct for that. So it looks very, very similar to the correction we did for the DC offset voltage problem with an integrator, except that we've added a resistor between the non-inverting input terminal and ground. So I feel like I have beat input bias currents and how to fix them to death. So long story short, put a resistor between the non-inverting input terminal and ground where the size of the resistor is just big enough to cancel out all the currents. So if IB1 and IB2 are not identical, yeah, if that's when you add that R2, you add the extra resistor in the feedback loop, which is just getting rid of more offset, which is exactly what it was doing when we had a input offset voltage. Yeah, they're still, so. Exactly right, but they shouldn't be doing much of anything, so I didn't bother going. Correct. All right, so the next thing I want to talk about is the finite bandwidth of op amps. And I'm going to do this largely pictorially. So let me open up another file here real quick. Let's go to so many things in the way. 223, just pulling up that data sheet for a real op amp. Open. There we go. And I think this one. All right, I'm going to scroll down to page 9, I think I have in my notes. We'll see. So much junk. All right. So our attention right now should be focused on this graph in the upper right-hand corner. All right. So in a ideal op amp, it has infinite gain over all frequencies, which means it has an infinite bandwidth. In a practical op amp, the bandwidth is finite. So we are going to define bandwidth really quickly here as the range of frequencies over which, let me write this down actually, that'll be better. So bandwidth is the frequency range over which the voltage gain is above 1 over the square root of 2 if we are working in units of volts per volt, or -3 decibels if we're looking at a Bode plot or something on the decibel scale of its maximum output value. So let's circle back around to this guy real quick. All right. So this plot here says it is the open loop large signal differential voltage amplification versus frequency. Okay. So at near DC, we have a large signal open loop voltage gain, AV, or excuse me, A naught, as we've been calling it in this class, of about 107 dB, which corresponds, let's see, if a gain of 10 is 20 dB and a gain of 100 is 40, 1,000, 100,000, so 10, 100, 1,000, 10,000, 100,000, a little bit more than 100,000. Sorry, I had to do the math there in a minute. So we have an open loop gain of a little bit more than 100,000 on this guy. I think the data sheet probably says it's somewhere around 200,000 actually. But that gain is only applicable for frequencies up to about 4 hertz. Right? Anything beyond that, and we see that the gain starts to roll off pretty significantly at roughly 20 decibels per decade. So what's good about that is it's the open loop gain that's falling down. So if we wanted to use this particular op amp, TI's MUA 741 op amp, and we wanted to design this circuit for a gain of, let's say, 10 decibels, we would simply come over here and we can see that roughly speaking, this is going to correspond to somewhere around 200 to 300 kilohertz. Our bandwidth increases as our gain goes down. That's because in a real op amp, the gain bandwidth product is a constant value, okay? So our bandwidth is defined as the total range of frequencies until our signal drops to 3 dB below what we want our maximum output to be. And we also have another figure of merit here So when we are at our frequency here, when we're looking at a gain of 0, this is FU, not trying to throw shade at anybody, but this is the unity gain frequency, because a gain of 0 decibels is exactly equal to a gain of 1 volt per volt. This unity gain frequency is exactly the same as our gain bandwidth product, because here the gain is 1, so our bandwidth is the rest of it, right? So if we want to, let's say in the textbook, there's a numerical example that if you use their numbers, you don't get the numerical answer they do, but if you use literally gain times bandwidth is equal, or gain 1 times bandwidth 1 is equal to gain 2 times bandwidth 2, you get their answer rather trivially. In the textbook, it says something about you have an open loop gain of 100 with a bandwidth of 1 megahertz, and you're trying to use that amp to get a closed loop gain of 16. So if you decrease the gain by roughly a factor of 6, what should you expect to happen to the bandwidth? It will increase by roughly a factor of 6. That's it. So there's a whole bunch of hippie math and crap in the book. Literally just remember gain bandwidth product is a constant and you can do everything you need to do, right? So if you have an op amp with an open loop gain of a couple of 100,000 like this guy, and you want a closed loop gain of 100, which would correspond to, let's see, 0, 10, 20, here's 40. Your bandwidth is around 10 kilohertz. Really easy to interpret this style of graph. So any questions on the finite bandwidth of an op amp? Yes. Exactly right. So with that in mind, actually, I have an LT Spice simulation prepared that we can kind of look at some things. Let me get my mouse out real quick. So I know it's been a hot minute since most of you guys took circuits 2, so I always use universal op amp 2 because it has all of these editable parameters. So I have set this guy up for an open loop gain of 200,000, a gain bandwidth product of 1 megahertz, and a slew rate of 100 megahertz because I don't want slew rate distortion to mess with what we're about to see. By the way, slew rate is literally what we're going to talk about next. So if I run my simulation right now, I have a 50 kilohertz sine wave. And I look at my input signal and my output signal. I can see that they effectively match, right? This is a simple unity gain buffer, so I should expect a gain of 1. At a frequency of 50 kilohertz, everything seems okay. There is a little bit of time shift between the two signals. That is due to the compensation capacitor inside. That is the reason why op amps have both finite bandwidth and a slew rate, meaning they can't process signals instantaneously. If we bump our frequency up to 100 kilohertz, I'll get a keyboard for this too. Everything's still looking pretty okay because we're well below the gain bandwidth product. Now we're at 1 megahertz and we start to see an appreciable decrease of voltage gain, right? So we should see a 1-to-1 ratio between the input signal and the output signal, but instead we are seeing that our output is at about 75% of where we would expect it. If we increase this further, we see that our gain has fallen down even more. And if I increase this further, it's going to be so damn busy on this time thing that we can't actually see anything that's going on. So this is a simulation exactly showing you what you observe in your 229 lab. The bandwidth of a real op-amp circuit is finite. And if you exceed the gain bandwidth product, so if the gain bandwidth product of your desired system is larger than the gain bandwidth product of your actual op-amp, you will not be able to achieve the gain you're looking for. All right, so the next thing that we are going to talk about, unless there's any other questions, is the slew rate. Okay. So because of the internal capacitances within an op-amp, a real op-amp cannot instantaneously change due to an abrupt change in large signal voltages. So I'm going to bring that data sheet up again real quick here, and we're going to look at this bottom graph on this page. So voltage follower, large signal pulse response. This is how the slew rate of an op-amp is measured. What they do is they put in a step function, right? So it's just a near instantaneous increase in a large signal voltage, and they measure the time it takes for the output to catch up. But they do it in a very, very specific way. Slew rate is measured by determining the amount of time it takes the signal to go from 10% of its final value to 90% of its final value. So in this case, that would mean a change from, so it's at -5, so a change from -4 to +4 would be that overall 80% change in the signal. And the time it takes for that to happen looks to be somewhere on the order of about 13 microseconds. This is mislabeled as milliseconds. So our change in voltage is 8 volts. Our change in time is around 13 microseconds. So somebody do the math and tell me what that's supposed to be. What's 8 over 13? Close to a half. Let's just throw something easy like that out, right? If we scroll up to page 7, the slew rate at unity gain is typically somewhere around ½ of a volt per microsecond. So we are interpreting that graph correctly. Now, we are not typically going to put pulses on op-amps. We might be trying to amplify sinusoidal signals and things like that. And the slew rate still absolutely matters, because when our signal crosses 0, be it positive zero crossing, meaning it's increasing, or a -0 crossing, meaning it's decreasing, it's at that point that our signal has the largest slope, which means slew rate can come into play. So I am going to change my simulation here, if I can find it. I'm going to drop this frequency back down to 50 kilohertz. And I'm going to change my slew rate to be 0.5 meg, which means 0.5 volts per microsecond, exactly what we saw on our data sheet. So if I run my simulation, again, I see our output signal and our input signal are very well matched, right? No appreciable distortion. If I bump it up to 100 kilohertz, now I can see something, some form of distortion, right? So what's happening is around the 0 crossing, our output signal can't change as fast as our input signal is changing. And so instead of getting a nice sinusoidal curve, it starts to look real linear right there until it catches up down here. And then it does the same thing around every 0 crossing. If we were to further increase our frequency, we get triangle waves. This means it's having such a hard time catching up with the changes that it's no longer even giving us anything remotely sinusoidal looking, okay? So while this can look similar to gain bandwidth product limitations because the amplitude is decreasing, it's a slew rate problem because we're no longer seeing the sinusoidal output that we're expecting. Our amplifier literally cannot catch up. That capacitor is too large for our the internal capacitances are too large for our amplifier to accurately process the information it's being fed. So that's a fundamental difference between gain bandwidth product and slew rate. They're both due to the internal capacitances, but they happen, or the effects they provide are different. All right, so just so we have some sort of mathematical representation here, there is an upper limit. Why don't pause that? To our slew rate, or what frequency of signals can be processed. There's one other thing I forgot to show you, but it'll be okay. So for our slew rate, let me give you a definition real quick. Maximum rate of change of an op-amp's output voltage. And for sinusoids specifically, our slew rate, SR, has to be greater than or equal to 2 pi times the frequency of the sinusoid multiplied by the peak value or amplitude of the sinusoid. Meaning, if I had lowered our amplitude, let's circle back here, right? I have a triangular wave. If I change this from having an amplitude of 1 to an amplitude of 0.5, peak value, and rerun it, it's not as much distortion as we observe because the slew rate distortion depends on both the frequency and the amplitude of the sinusoid. Okay, that's what I was trying to get at. All right, we have 20 minutes left. So the textbook has about a page and a half, including an example problem on the effects of a finite input resistance and finite output resistance on a practical op-amp circuit. We actually covered all that crap way back in circuits 2. They do one problem and it effectively says having a finite input resistance and output resistance winds up introducing gain error, which is exactly what we observed way back in circuits 2. So I do have something prepared, but since we're running a little bit low on time, all those circuits 2 notes are on my YouTube channel. It would be lecture 4 if you wanted to go through and refresh yourself on that. So the last thing that I want to talk about then is the quiz that I uploaded today. Did I spell it right? Yes. So if we go to our 336 page and we go to today's class meeting, today is the 19th, I believe. Yep. There is a quiz that has been uploaded and there's an online submission portal. It is due at 5 p.m. on March 31st. So that is the Wednesday after we get back from our Easter holiday. So let's open this guy up and take a look at it real quick. One thing that I want to point out here says group members' names, meaning that you are allowed to collaborate with each other on this quiz. 3-person teams. I think there are 23 students total in this class, so that means that there will be one 2-person team if everybody else does 3-man teams, but we'll figure it out. So absolute maximum of 3 people. I don't care if you do 2-people teams or if you decide you want to work the whole damn thing yourself. That's perfectly reasonable by me, but no more than 3 people collaborating together. All right, so let's take a look at this guy just real quick. Question 1, is this a non-inverting or inverting amplifier? Anybody care to venture a guess? Pardon? Non-inverting. Why is it non-inverting? That's the second part. The input's on the non-inverting terminal. That is as much information as I need. Absolutely correct. Problem 2, what is the ideal voltage gain, input impedance, and output impedance of the circuit? Show formulas or otherwise justify your answers. I would argue that the otherwise justify your values thing makes a lot more sense here. So what's the ideal open loop gain of this op-amp circuit? If it's an ideal op-amp, the answer should be infinity, right? What's the ideal closed loop gain? All right, so you're just throwing out a whole bunch of things at me. Let's try again. Also, the gain should not have Vn in it since the gain by definition is V out divided by Vn. Yeah, 1 plus R1 over R2. So in this case, 10,000 over 100 is 101 gain, right? Yeah. What is the ideal input impedance? Pardon? Yeah. What's the idea? Can you justify that answer? Let's start there. Circuits 2. Okay, fair enough. So our input signal, if this is an ideal op-amp, sees an open circuit. So that's why it has an infinite input resistance. All right. Output resistance, what should it be ideally? 0. Why? That's where it gets a little harder, okay? If you review the circuits 2 material for every one of these practical op-amp circuits that we did, it didn't matter what our R out value was, the output resistance measured looking into the output terminal was typically somewhere around 0. For an ideal op-amp, we effectively have a short circuit in parallel with this network, which is going to be exactly 0. Let's see, draw the equivalent circuit of this amplifier, assuming balanced input bias currents of 2 milliamps. So those would be pretty dang big input bias currents. So could you draw this with the current sources in there? I certainly hope so, because I drew it like 4 times. One between here and ground, one between here and ground, you're good to go. You decide to add a resistor to the input network. Is the resistor in series or parallel with the input port? I feel like I said this at least 5 times. What's the answer? Yeah, so your resistor to correct for the input bias currents, is it in series or in parallel with the input? It's in series with the non-inverting input every single time, in series with the non-inverting input. And its value should be R1 in parallel with R2. Okay, so what value of resistor will neutralize the non-ideal effect? The input bias current has on the 0 input response. So what is meant by 0 input response is literally Vn is equal to 0. That is what we went through today. Rework the problem, replacing R2 with a capacitor. So it goes from a inverting amplifier to something like a non-inverting integrator. So a non-inverting integrator, what that's going to do is it's going to have a positive voltage gain. And what you're going to observe is that it's the input signal plus the integral of the input signal scaled by a factor. That's very, very easy to derive. So I'm not too concerned about it. And you can get that just from looking at it as from an impedance relationship, where it's a non-inverting amplifier where you have the voltage gain is 1 plus Z1 over Z2 for this guy. So that's not real difficult. How does the addition of the input bias current affect the linearity of the circuit? That's a good question. You guys figure that out. I'm not going to answer literally all 7 of them for you. So, like I said, this is your quiz. You can work on it in teams of 3. You have a week and a couple of days to work on it. So, I don't know, any questions? Kind of out of stuff to talk about for today. All right, so on Monday, we are going to begin talking about cascode current sources. So if you could briefly review BJT and MOSFET current sources only, and we'll build from there. So should take 10, 15 minutes tops to review that. If you don't understand how current sources are implemented using BJTs and MOSFETs, then everything's going to be over your head. So, all right, see you guys on Monday. Where's the roll sheet? Is